Hello and welcome on this tutorial of our online lifecycle impact assessment tool that we call Calculator. My name is Romain Saki and I am the lead developer of the tool, which has been in its most part developed by the Paul Scherrer Institute in Switzerland. We'll try to keep this tutorial relatively short, between 10 and 15 minutes. So um, this tool is offered in two versions, the online version, which is where we are now at calculator.psi.ch, as well as a Python library version that we describe here and for which you can find the source code and some documentation on our GitHub repository. Okay, so it is the tool that is constantly evolving. We bring many fixes to it all the time, and we are also quite transparent about this. You'll find on the website some information, even this little explainer video. The tool allows the comparative assessment of 9 different powertrain technologies, from battery electric car to combustion cars, hybrid, plug-in hybrid, fuel cell, etc., for different size classes, from city cars to SUVs and vans, for different driving cycles, whether we should calculate the fuel consumption for a mostly urban driving pattern or highway or a mix of both. You can, of course, modify a good number of parameters. You can choose different chemistries for battery electric cars. We have electric mixes over close to 90 different countries, and we can run analysis for anywhere between 2000 and 2050. Here is the team behind Calculator. So that team is from the Technology Assessment Group at the Paul Scherrer Institute. And you're welcome to drop us an email, or if you have questions on how to use the tool, through this contact form. All right, so let's dive right into it. So you can start by clicking this button. Here you have several options. We are concerned by those three. Basically, the first one leads you directly to results, comparative results between a diesel car, a gasoline car, a compressed gas car, and a battery electric vehicle for 2020 in the country you're located in. So for me, it says Switzerland because this is where I'm located at right now. Um, this option goes a bit more into details into the parameters of the car, but again, relatively simple. They will lead to the same results presented here. And this option lets you build your scenario from scratch. And this is what we are going to do. To access this level of access, or this one, you will need to create an account. So I've created an account already and I'm logged in, so there is no problem here. Again, creating an account is just completely free, and everyone can do it. All right, so we land on the configuration page. Okay, so let's start by clicking on the car icon. In the future, other vehicles would be provided, but for now, it's just passenger cars. So we need to select the cars we want to be comparing. So let's compare cars produced in 2020. We can compare a gasoline car with a gas car and maybe an electric car and a fuel cell car. Maybe the size should be compact. That is more or less equivalent to a Volkswagen Golf, for you to have an idea. Now some parameters for the use phase. Here we can select the driving cycles we want to use um, that will basically be used to calculate the fuel consumptions of our cars. So here it shows the details of the driving cycle, where you have the speed on the y-axis and the duration of the driving cycle. The WLTC driving cycle is the standard one used all around the globe and in Europe as well. Um, and here you have subsections of the WLTC driving cycle. So for example, this subsection 3.1 is mostly urban driving. You can see that we stay beneath 50 kilometers per hour. If you go for the regular WLTC driving cycle, you have a little bit of urban driving and then extra urban driving and then highway driving where we have peaks at 130 kilometers per hour. Here we are asked to choose a country where we want to conduct our analysis. So let's choose, for example, Spain. Right, so now we are asked to choose the electricity mix we want to use, and the electricity mix will be used for charging batteries when we select battery electric cars, but it can also be used if we choose fuel cell cars because we need, if we select the supply of hydrogen from electrolyzers, these electrolyzers will be requiring electricity, and that's the mix that is going to be used. And it will also be used if we choose to run our uh, gasoline car on synthetic fuel, because synthetic fuel will require hydrogen made from electrolysis, and it will also require um, to extract carbon via direct air capture, and this will require electricity as well. All right, so the mix shown here is basically the suggested mix for the year 2020 for Spain. You can leave it as it is, or you can also set it to 0 and use a special mix. For example, let's say uh, 50% wind power and uh, I don't know, 50% hydroelectricity. That's going to be pretty green. Then we can choose the number of passengers. Let's say 2 persons. We can choose the lifetime of the car, which is a pretty important parameter because in the end we will normalize the impact of our cars by the number of kilometers they drive to obtain results per vehicle kilometer. Then we can choose how much luggage we have in this car and also the annual mileage. Um, then we have some technical parameters for the cars we've selected. For example, in this section, we can set the engine efficiency of the different cars, the drivetrain efficiency, and also for electric powertrain, we can here set the battery discharge efficiency as well as the efficiency of the fuel cell stack. And the product of this different efficiency gives us the tank to wheel efficiency, which is basically how much megajoules, for example, do I need in my tank or in my battery to have a megajoule effectively transmitted at the wheel. So, for example, the tank to wheel efficiency of 24% means if I want a megajoule of energy transmitted to my wheels, I will need a I will need 4 times that amount in my fuel tank. So around 4 megajoules because some of it will be lost as heat by the engine and some of it will be lost through friction through the drivetrain, the gearbox and the transmission shaft, etc. Of course, you can modify these values, or if you don't really have an idea about them, you can just keep the default values. Of course, if we had selected 2050 as a year of analysis, these values will be a bit different because we also model expected technological improvement. Here we have a section dedicated to the battery electric car that will only be displayed if you have selected battery electric cars. And here we offer the possibility to dimension the battery you want your car to be equipped with. So you can modify the mass of the battery. You can also modify the energy density of the battery cell. That is how much uh, energy can be saved per kilo of battery cell. And these two parameters will define the capacity of your battery. Of course, as we go in the future, the battery cell, the energy density of the battery cell will improve, meaning that for a given mass, you can pack in more energy, and this will improve the range of your battery electric vehicle. And you can also set the lifetime of the battery and choose the chemistry and where the battery is produced, which will influence which type of heat and electricity will be used to manufacture the battery, which is quite energy intensive. Um, if you set a battery lifetime that is inferior to the vehicle lifetime, then the model will account for a second battery. Um, And but of course it will only account for a fraction of the second battery, which is needed to complete the vehicle lifetime. If you wanted to consider the environmental burden of the whole second battery, then you need to set this lifetime to be exactly half of the vehicle lifetime. So if we think the car will last 200,000 kilometers, and by setting the lifetime of the battery to 100,000, it means that we will use a second battery, and that the entirety of the environmental burden of the second battery will be attributed to the car. And here we have a section about fuel blends where you can adjust the fuel blends. We have regular fuels like gasoline, we have biofuels from crop residues, etc. And we have synthetic fuels that, again, they use hydrogen made from electricity. Um, Same for gas. We have regular natural gas, we have biogas, and we have synthetic gas. And same for hydrogen. We have hydrogen from steam methane reforming, from electrolysis, which we need to select if we want the electricity mix specified above to be considered. We have also from steam methane reforming of biogas, from coal gasification, and some other options with carbon capture and storage. Okay, then we have some buttons at the top. When this button is green, it means you're ready to launch your calculation, which we are going to do now. Ah, one of the fuel blends has both primary and secondary fuels set to the same, and that's hydrogen. So this one needs to be different, and if we don't want to use it, we just set it to 0. So in this case, 100% is hydrogen from electrolysis. This should work now. Okay, so this will take a few seconds for the server to compute the results. In the meanwhile, we can see that we have some other buttons up there. We have one called modeling and assumption that leads you to the documentation of the tool, where we explain, how things are calculated and so on. And also it shows the source code and things like that. Yeah. Then we have some other buttons. Share configuration. If you press that, you will download a small text file. Okay, here it says that um, once if you download this, okay, here our calculation is about to be over, so we will click on the small pop-up once it appears. Calculation progress 100%. Right, we will be redirected to the results page, but I just wanted to explain the use of this small text file that we downloaded by pressing share configuration. Its use is that the next time you come back to this configuration page, which is now blank because I refreshed it, you can drag and drop this configuration file and find the exact configuration as you left it. That's quite convenient to reproduce results or to share your configuration with other users. Anyway, now we end up on the results page. We have a number of buttons, but I believe their meaning is quite straightforward. There is also this option to export the inventories of the car models you've just built to be imported in other LCA softwares to do more, to do deeper analysis maybe. All right. Now the first section presents what we call midpoint environmental indicators like climate change, uh, fine particle formation, and these kind of things. Or maybe I zoomed out a little too much here. Not all of these indicators have the same amount of robustness. So, for example, climate change, depletion of fossil fuels, depletion of ozone layer, these are quite robust environmental indicators. And then we have some least robust ones, and then we have the least robust indicators down here. We have an explanation on what these indicators are showing and if there are any specific assumptions that affect results for this specific indicator. We describe it here. All right, so if you click on the results on the different indicators, you have the corresponding results showing up. You can also um, isolate some of the contribution categories. For example, we have direct emissions here, which of course we have none for electric vehicles, but we have some for gas and petrol vehicles. Um, you can, for example, if you want to isolate the impact coming from preparing the fuel, you can click out the other categories, and this will show you the impact, the CO2 associated for preparing the fuel. In the case of the fuel cell car, and that will be the impact of preparing the hydrogen, which is strongly correlated to the electricity supply. And in the case of the electric car, that's the impact of producing the electricity. In the case of our natural gas car, that's the impact associated to producing and supplying the natural gas. And for our gasoline car, the impact associated to producing the gasoline. All right. Um, Here, this graph on the left shows the cumulated impact over the lifetime. So we start at kilometer zero, which shows the impact related to producing the car. And then we have the impact as we are driving the car up to 200,000 kilometers, which was the lifetime we set. So this is very convenient to see at which point do we have break even with other options. For example, in this case, we see that the electric car break evens with the gasoline car at about 30,000 kilometers, after which it's net CO2 savings. Okay, this next graph here shows results if we normalize them by the average impact of one person per year. This is really useful to sort of highlight which impacts are more, more important compared to others. Um, for example, here we have selected only the most recommended ones by the European Commission. It's telling us that among the cars we've selected here, that for example, the gasoline car will emit climate like greenhouse gas emissions up to 3.7 millionths of what an average person would emit in 1 year. Of course, these are results per kilometer. But that is telling us that maybe climate change is already more important as a higher priority than depletion of ozone layer uh, and formation of fine particles being somewhere in between. And then the vehicles that have the least area in these spirographs are of course the best option. Okay, next graph shows because here we are looking at midpoint indicators and there are like 22 of them. It's not very easy to make a choice because I mean, should we prefer a car that has the lowest climate change impact but a pretty high impact in terms of smoke formation or vice versa? It's not straightforward because smoke formation might be equally as important as climate change. And that's why here we reduce the number of these indicators to 4 of them, which we call endpoint indicators, and which are human health, ecosystem, resource depletion, and cost of ownership. And we let the user set some preference. So for example, if for you cost of ownership is not important, you can reduce it to 0, and then you can share the importance of the results maybe evenly between human health, ecosystem, and resource depletion. And then you have corresponding um, impacts here shown in this pie graph on the left. So here it shows the contribution of the midpoint indicators in the endpoint indicators, and here it shows uh, the sum of the endpoint indicators because they are expressed in a similar unit now. So for example, for this distribution of importance between human health impact, ecosystem impact, and resource depletion, the winner is apparently the fuel cell vehicle, right? Because it has the lowest point impacts. Okay, here we propose a benchmark in terms of life cycle budget. For example, how long can I drive each of the vehicles I selected if my budget is 1 kilo of CO2? Well, the winner would be the electric car, with which you can drive 7.6 kilometers before you emit 1 kilo of CO2 equivalent. Or if my budget is €1, In that case, that would be the gas car, or 1 liter of petrol equivalent. And then we have some other indicators that would show, for example, the second by second energy consumption of the cars we have designed according to the driving cycle we have selected. And here is a simple graph that shows climate change per kilometer on the y-axis and cost of ownership per kilometer on the x-axis. So of course the ideal vehicles will be closer to the point zero here. So for example, we have the gas car that is cost 30 cents of euro per kilometer and emits 0.24 kilograms of CO2 per kilometer. And here we have the electric car that emits a bit less, but is a bit more expensive. Okay, that was it. I hope I have answered most of the questions. I invite you to play around with the tool and um, to drop us an email if you have any specific questions. Thank you very much for your attention.